Hi everyone, we're going to talk today about certificates. I'm going to start from assuming that you're really good at math, and we're going to solve multi-dimensional elliptic curve to do that. The problem is simple. I like coffee. Don't tell anyone. And I want to order some coffee. And there is Alice who is going to make some coffee because she works at the coffee shop. Unfortunately, I have very specific details about coffee that I don't want to share with the whole world. How do I talk to Alice and tell her to do that? This is where there is a problem. There is Charlie. Charlie is not a nice guy. And I'm not wanting to hear what I'm told, my order to Alice. So, how do we do that? I know math, 2 + 2 = 7. So, we can fix that. Yes, I know, it's not right. So, here's what we do. As you can see, there is Bob and Alice both have public and private keys. And if you look into that and multiply that in a Montgomery curve, and she's going to multiply that with this Montgomery curve, we're going to get the right value. If you can do that in your head, congratulations, you should go join a monastery. Okay? But the basic idea is that you have the private key and the public key for both of them. There is an operation that we can use to get to the right value. Let's see that. Here is the point. So here is Alice public private key, Bob public private key. We'll say give me the public key info and set it to the other side. And now this is the remote Alice, the remote Bob, and we can call this guy. Derive key material from my private key, and the other side public key. This is called a Diffie-Hellman. There are several versions of that. Right now we're using something called Elliptic Curve Diffie-Hellman. There is also RSA, but RSA require primes, big primes. They're much larger, and this is much more easier to work with, also from a computational perspective. Questions? This is the end result. This is a 256 bits key. What am I going to be doing with that?
This is a symmetric key.
This is what we've done now is asymmetric work. We got this value, and now we can take this value and use it as a symmetric key for encryption. So this is the next stage. So let's look at the 2 steps. I have this network string here. I create an AES and generate a new IV. And then I create an encryptor with Alice key and the IV. And I read the here remote IV and create a decryptor for reading and writing. What's the point here? Encryption is a mathematical operation. If I encrypt the same value twice, what am I going to get? Using the same key, I encrypt the same value twice.
The decrypted value.
No. I tell you attack the DOM. And I tell Aviv attack the DOM using the same key. What message is he going to get and what message are you going to get?
Same key?
Same key.
Same value?
Same message, yeah.
And then you get the same?
Yeah, I'm getting the same thing. Okay. And that is a problem. Why? Because he can look, he knows, so in this case, he knows the key. that let's assume that our Charlie is Shiran. She intercepts a message, doesn't know the key, but she sees that he attacks at home. Tomorrow I send the same message to Aviv. She intercepts the same message. If it's the same message, and I know I observe your behavior, okay, he's going to attack it on. That's one of the effects. Other aspect of that is that if you encrypted with the same key multiple values, you can XOR them together and get the XOR of the decrypted text. And the reason, and basically, it means that the moment that I have that, I unlock everything. So a very important aspect in encrypting is that encrypting the same value with the same key must result in different values. I'm doing that using something called initialization vector or the nonce. And the idea here is that the nonce, which is number only used once, or the IV, is some random value that they generate, which is not a secret. But I mix that into the encryption process, and it ensures that for different IVs, for different nonsense, even the same material is going to be different under the same encryption key. So the result of this nice thing is that now I have read and write operations that are free and fun and a bunch of other stuff like that. Okay? Good. Now I can get my coffee. There's a problem. What's the problem? I ask for coffee and I got tea. But we are secure, by the way. Bobby is talking securely. Alice is talking securely. That's right. I can prove that this is secure. What's the problem?
You're both talking securely with Charlie.
Yes. So we are talking securely to each other, and this is
You can switch.
Sorry?
You can switch the message. It's sent from Bob to Alice. So
he can intercept all this communication. He can change whatever he wants, and in a way that is completely undetectable to me. That's not a good idea. How do we fix that? That's the question. How do we fix that?
It uses a certificate, so the person you're trying to connect to can prove
Okay,
that.
but for now, I don't know what certificates are.
Okay.
So right now you said, okay, use a magic box.
Okay.
What's inside the magic box?
Secure socket.
Secure socket layer, which is an old name for security, which uses this thing.
Some system of trust.
Hmm?
Like you need to know that you trust.
So one way of doing that would be to go and ask. And that's nice, but it is not sustainable. Because there is Alice and Jane and Dana and whoever else is working there. But there is David. That is nice. He's kind of a coffee snob. But he has some really important properties. In particular, he has this. His public key. What can I do with that? So I don't need to trust Jane, Dana, and Alice. I can just trust Dale. What happens there? Well, for one thing, I don't want to have Dale give his private key to Alice.
you can encrypt some message to you, and you can decrypt it, and you can see that only him can encrypt this message.
Okay, so remember that for public keys, for asymmetric encryption, there are two main purposes. One is encryption, the other one is signing. So let's see what we can do with signatures. Here is the code. what we see here, this is Alice. This is her public key. What did Dale do?
They send the sign that Alice got the message.
No, Dale signed Alice public key.
Yeah.
Okay, not the message.
Yeah.
He signed a public key for Alice. This is the signature.
He said that both can trust Alice.
It's right now the only thing that he says that there is a signature of Alice public key. So let's see what happens now. Bob knows Dale. And Dale gave Alice his signature over her public key. So what do we do now? This is Dale's public key. And this is this value here, AG something something. And now we're doing this thing. Okay? We are saying verify the signature. So we are passing, here is Alice's public key, as I note. Here is the expected signature and the hash that we don't care about. At the end of the day, what does this give me?
To be sure that Alice works for Dale.
What it gives me is that now I can verify that Alice is the person who is signed by them. Now notice there are multiple steps in the process. So when I start talking to Alice, I do this. So getting her public key from someone. And here I verify that this public key was signed by someone I trust. So I need to get both Alice's public key and their signature of her public key in order to
compare them.
to verify the data, not compare them. There is a reason this is different with cryptography and encryption. We really want to avoid using the term comparisons because that exposes you to comparing strings and values, and then you are leaking timing data. So right now in here, I'm saying, okay, let's import the public key, verify the signature. If the signature is okay, I can go and basically derive the key material and get to the secret key that I have here. Okay? So far, so good. It's wonderful. No problem. Oh, no problem. What next? Right now, I have a system that I will trust Alice because I trust Dale and he signed her public key. What other things do I have to worry about? I can also trust Jane, and I can also trust John, and I'm sure that Charlie cannot listen to my coffee order. What's more?
I thought maybe they can signature Charlie's key, but I'm not sure.
So in some cases, it may be the case that you want to. So in this case, Bob want to authenticate Alice because he wants to give her his secure coffee order. Alice doesn't care if the coffee order goes to Bob or to Aviv, because both of them are paying. Who cares? Sometimes you do care. If I'm asking you, give me my, if I go to the doctor and give me my blood works, I don't want him to give me Aviv's blood works, and Aviv doesn't want my doctor to give me his blood works. Okay? So now we need to authenticate to the other side. but the client make it. And yes, you can do that with a certificate as well. But for now, let's ignore that and talk about what other things do I have to do. For example, Alice is pissed off and goes walking for the competition. What's the problem?
She still has the old key.
She still has the key. She's still verified. There's no way to revoke that. So this key is very easy, but we need something more. So let's look at this one. So now we have more details. Who is she? The validity period to make sure that she doesn't have a blank check for everything. The role, whatever, etc. What are we missing? What are you looking at and saying, this should be here?
The public key, maybe no.
There is no public key, so we are not saying who signed it. And yeah, we should also have the actual public key. You're absolutely correct. I was so focused on that, I completely forgot. Yeah, the public key that this is the actual signature should be. What else?
Maybe you signed it.
That's really interesting. So let's go and look in more details. Okay. So then he's really, really successful. He opens many branches. That's a problem. Now we have too many employees to sign all of them manually. So now we need to delegate. And we're doing it like this. So there is Dave. Apparently he changed his name. And we have all of those. Those are supposed to be the same thing, but I guess the Polish will laugh at me when you see that. So how do I create a secure system now? I have to do something like this. So let's look into that in detail. At the bottommost layer, we have Alice. Alice is signed by 40 years old. He is the signature. And now I can see something that where I can get their public signature. I go to this guy. This is copy and code. Again, notice the validity period. This can sign one level down. Again, sign here. And go up. This is their coffee, and this is signed by them. Same logic. And again, I actually forgot the public key. Why is it there here?
Maybe
Think about it. Why do I trust Alice?
because you trust the
Because copy and code.
no, you
Why?
trust Hadera.
I don't trust their coffee.
You trust them.
Same.
I trust them. So there isn't here because either I already trust him or I don't. If I don't trust him, it's not meaningful to say. So I trust Dale or Dave or whatever. And now I have Dale created sign this. This is that he trusts Hadera Coffee to sign not just employees, but also shops that would sign on employees. Okay, you follow what's going on? Another issue here is signature versus the signer. What's the signature?
String. It's
Just some binary data that represent the signer fees. And now we have a signer. But notice that we don't have the public key of the signer. Why is that? Because we don't need to. The because we can go here
And get
and get
the
a public key.
Yeah.
And then we do this. Now, in practice, it's more complex because what you actually get here is this whole document, which include the public key, also include other things. So consider the following scenario. Let's say that this ends on December 31, and I update this, so before the end of this, I update this URL to say, oh, this is from an end date of December 4th to December 4th, 2024. So this is not the same document that was used to sign this one, but it is the same key under the same name. And the reason this matters is that this allows me to do all sorts of interesting things. For example, I trust Dale, and Aviv trusts Monica. Now, if Aviv wants to go and buy something from Alice, he would go and say, oh, I don't trust him. But now we can start playing interesting games. Dave and Monica both sign a certificate. They sign the copy certificate. And then that certificate is used to sign all the way down. This is called cross-signing. And because the actual certificate does not contain the actual certificate does not contain the signature of its parent, as long as the public key and the name match, I can sign both of them. You follow?
Yeah.
Okay. So this is a nice trick that is enabled by this. So JSON is a horrible format for doing this sort of thing. Why? Let's say I switch the order of this. Do I need to change the signature? No. How do you know that? For fun, assume that you have someone who is malicious and they need something like, okay, I'm going to put 2 start dates here. One here and one here. You start reading, you validate this one. The client starts reading, they validate this one. So there is a whole bunch of really annoying scenarios that you have to deal with. JSON is a pretty bad format for this one. If you go read JWT, you can see a whole lot of fun around that. And there have been security vulnerabilities around this. We typically use external certificates, which are using a format, they're using something called ASN.1 encoding, which is basically, you can think about it very similar to JSON, but binary and annoying. There are a couple of encoding there and there and a bunch of other stuff like that, but it doesn't actually matter. Conceptually, it's the exact same thing. Let's go for a second and inspect a certificate. And so here is a certificate. And you can see this is the data, here are the signature algorithm, the public key, etc. And there are all sorts of fields here that matters quite a lot. But they're just fields in the document. And not really that interesting. Notice that in this case, you can see that this is the issuer. It was issued by this team. And this is how it was issued, and that's about it. If you want to grab the issuer, you can use this thing, so-called authority information access. And
This is
grab.
a certificate of the authority who signed.
This is the certificate who sign this one, yes.
Okay.
And you can go into that and read that and go. Typically, there are 3 layers: the root authority, the intermediate, and the leaf certificate.
So when you sign only the key, or
You signed all of this,
all of, oh, okay.
all of this, not just the key. This is important.
Okay.
I trust you to be shahar for the next 2 days.
Because you need the dates.
So yeah, the dates are absolutely part of what I'm signing.
Okay.
Also, notice here, those are what domains do I have for you. So I trust all of that. That's the role of the certificate authority to ensure this. Okay. So there's a lot of fields that matters on what you do, how you do, etc. Of particular interest is whatever this certificate can sign a child certificate or not. Now, it's important to understand that none of that relates to the math part. Okay, so I can take a certificate who is not allowed to sign a child certificate and still sign that. And it will work and produce a cryptographically valid result. If I try to validate using a conforming certificate validation procedure, it says, oh no, on this level, this certificate cannot sign a child certificate. I'm not trusting you on that. So I would abort. But we are actually using that a lot in our case. Typically, when we use a certificate in RavenDB, they are used from Let's Encrypt. And let's look at Let's Encrypt certificate.
Private server, trust,
One second, let's
encrypt, okay.
let's look into that. Here is a certificate. And now you can see this is, you can see, yeah, I don't know why it says RavenDB community. 1 second, let's see. Okay, let's go a little bit deeper, and we're looking for subject alternative names. Let's do this. Let's explore this. Now, where did I put it? Very certain I just exported this somewhere. Yeah, let's try it again. Pictures for some reason. Okay. This is the certificate part, and now we have subject. Okay. Okay, now we can see this. You can see that this is actually a certificate that was issued for multiple domains. RavenDB Net, RavenDB community, etc. When I look at the certification part, this is what it looks like. So this is for RavenDB community. This is the R3. This is the intermediate certificate used by Let's Encrypt. And this is the root certificate of Let's Encrypt, which is trusted by this machine. Okay. And we can go here and look at key usage. What am I supposed to do? Digital signature, key enrichment. What am I supposed to be doing it? This is an entity certificate. We're not allowed to sign anything. Now, I can take that and sign additional certificate with that. And we do that all the time with RavenDB because we use the server certificate to sign the certificate, the client certificate. But the point here is that when we do that on our own, using our own code, our own logic. Now, the signer publicly is not in the cell because it is in because we don't want that. We want to have more flexibility to be able to do cross signing and things like that. Now, there is this field, authority information access, that I can use to get the certificate. Now, think about what this means. I go and talk to Liam and tell him who you are, and he's give me a certificate. And that certificate is signed by Shachar. And that certificate, and Shachar's certificate is then signed by Moran, who I trust. So now, if I'm talking to Liam, what options do I have to enforce that chain of trust? Think about it. What are my options? There are two of those. One of them is that when I talk to Liam, he gives me his certificate. He says, okay, I need to talk to Shachar to get his certificate and validate that. So that means another network hop. That's a problem. Or when he's sending me his certificate, he's going to send me the parent certificate as well. So in one network round trip, I can get everything. Certificates typically use one of two options. There is RSA, and there is Elliptic Curve Cryptography. Why does it matter? RSA nowadays is 2 to 4K in size, whereas the ECC certificate are far smaller. Now, it doesn't matter that much, right? 4K to 100 bytes.
Matter because if you pass all the certificates, you need.
I typically need to pass 2. But it means that it's a difference between having to pass 8, 10 kilobytes and 1 kilobyte, 2 kilobytes. That actually ends up mattering a lot, especially if you're on a mobile, small devices, stuff like that. So there is a huge shift toward moving to elliptic curve cryptography. Another aspect is that almost all of the complexity is how do you look at the fields and the rules around them and something like that. The actual cryptography, the actual cryptographic API is really simple. The cryptography is go to multi-dimensional math. There's a lot of really fun things. No one bothers to do that. So, practically speaking, who owns certificates?
Who owns a certificate?
Who owns certificates? Who gets to make decisions on certificates?
The owner or something.
No. Google.
Okay.
Google owns certificates.
Okay.
Why? For a very simple reason. The primary use case for certificate today is for browsers. Google produces Chrome, and everything that goes into Chrome is basically a de facto standard. It used to be Firefox. A lot of the discussions are still handled on the Mozilla group. But basically, they get to say, okay, Chrome, starting for an X, will do this or that, and the industry aligns on that. There's a lot of really complicated rules and politics around that. For example, who is a root certificate? If we are looking from the perspective of Windows, that comes in the box. I can install from the Active Directory, I can install a root certificate on the domain machines. But if not, the person who is making the decision is some guy in Microsoft. And Mozilla and Firefox also have the same situation. Chrome tend to rely on the OS store, but not always. And a large part of that is that there is such a huge trust boundary for the root certificates that is utterly ridiculous. Let me show you something. Who do I trust above all else? And this one?
The use of a personal.
No, I don't want this. I want trustable certificate authority. So this one. So how about no liability accepted from Verizon? Verizon? VeriFi, sorry. And at some point, this is, I think, a Chinese company. There's quite a lot of that. Who is Baltimore Cyber Trust? And how do they relate to the CIA, etc.? So there is quite a lot of stuff here, which is weird. And now you have to consider what's going on. Someone on the line, you have some noise. That it would be very beneficial to not have noise. Lev, I think that's you, because you're only one not muted. Okay. Where was I? So certificate authority have a tremendous level of responsibility, and that's a problem because if you are certificate authority, you can try talk to Google, and they can redirect you to somewhere else. At some point, there was a certificate, widely distributed certificate authority owned by the Libyan government. I don't have a high degree of trust there. So this is the problem of trust. How do I trust? How do I trust that who you say well? And how do I trust the underlying system? And eventually it settles all the way down. So let's talk about how do I mitigate those issues. Something really important. Certificate may be stolen or lost, so I want a short validity period. Right now, Google said we do not trust any certificate that is longer than 1 year. Just if you give me a certificate that is longer than 1 year, that was issued after some period of time, it's untrustworthy. And there's a whole bunch of other stuff like that. Then you have things like revocation list and online certificate status, all of other stuff like that. I will touch it in a bit. But let's first talk about this evil guy that managed to get to be a certificate authority, an evil one. How do I ensure that even under evil certificate authority, I have some level of protection? The answer to that is there is something called certificate transparency. So when you issue a certificate, one of the actions undertaken by certificate authority is to register that in the public ledger. This is one of those cases where we actually use the blockchain on a more or less proper fashion, except that it's not a blockchain. And basically, in order for me to process a certificate, you issue a certificate, it is valid for 3 hours or so, I don't know the actual now, but it's a short amount of time. And then we require to be able to find it in the certificate transparency. And the way that it's typically done is that as part of the generation of the certificate, I register that in the certificate transparency log and add that signature to the certificate itself. At that point, it means that as a client, I can say I only trust certificates that have been published to the certificate transparency log. But that's the only thing that it does. How does it help us? It helps us show that you can be evil, but you must do that in public. That's the only thing that it does. You have to be evil in public. What does it mean? I want to pretend to be Google.com, and I'm evil. I can issue a certificate that you would trust for Google.com. Problem. In order to trust me, you need that to be registered in the transparency law, which is public, which means that Google monitors that and says, this certificate that I'm not familiar with, how did it come about? We make extensive use of certificates, and at one point we actually got a letter from a lawyer threatening to sue us for using a certificate that was the domain name of a particular company. When we dug down into what's going on there, it was actually a project for that company by a team there that we just generated. And so that's that. And that's basically, you can be evil, but you will be discovered and punished, and that limits what you can do. Now, I want to talk about perfect forward secrecy. Let's talk about this for a second. I want to talk to Liel. Okay. And what am I going to send to Liel to talk to him? Securely.
Request.
Okay, and how do I ensure that no one can listen to that?
Encrypted message.
How do I ensure that they have the right key?
You need to get first the certificate from there.
So I need to get his public key.
Yeah.
I need to send him my public key in order to do that, right? Now, assume that Aviv is listening over the network. Public keys has been exchanged. So far, so good. But he cannot intercept the actual communication. Perfect. Everyone is happy. Problem. Took FBI, police, whatever. I get the private key of Liam. What happens then? I have his private key. I have my public key of the intercepted communication. What can I do then? I can derive the decryption key for the communication. Follow? At which point I can read everything. This is considered to be a bad idea.
And how did you get a private key?
Yeah.
I grabbed his machine.
Oh, okay, just
Okay, so in this threat model, you have to consider that Aviv is listening, and then we got his physical keys.
okay.
We got the actual machine. So I have the intercepted communication, and I have the private key. I already sent my public key to him as part of the negotiation. Public key plus private key, decryption key, I'm good. How do I handle that? Sorry?
The digits, can't remember.
Nonce?
Yeah.
No, but again, Nonce is not private, it's public. So here is what I'm doing. When I'm talking to Liel is going to do the following thing. He's going to generate something called ephemeral keeper. Just invent something out of whole cloth. Right, we're good. he uses that keeper to talk to me and sign that keeper with his certificate that proves that he has the actual private key for the certificate that he gave me. He never saved that keeper over a long-term basis.
So this is the nonce, no?
No, this is not the nonce. This is the asymmetric key negotiation. So remember, private key, public key together gives me the symmetric key.
You don't use this value for like writing the symmetric key?
Let's go back.
This is before the asymmetric?
This is this part. Okay. Remember, Alice and Bob have public key, private keys, and use them to derive that. Okay. And now I need to verify that this is who we say we are. So we use this thing. Here is the funny part. If I do it like this, I have a static key. I always use Alice public key. That's a bad idea. Because if she loses her private key, I can intercept all of the communication. So here's what happens. When I talk to Alice, she generates a random keeper.
Based by
Sorry?
the keeper is based by what?
Just random keeper.
Okay.
Not based on anything. Not trusted anything. Now she's doing the following. The communication that we do goes like this. Here is my certificate. Here is my public key. Here is the signature of that public key by that certificate. So you actually have, this is the certificate. This is a public key, not related to this. This is the signature of the public key using the certificate. When I need to, so I have to do two steps. First, I have to validate that using this certificate, which contains the public key, I can validate that this public key that I got was signed by this certificate. This tells you nothing about trust, just that this public key was generated by this. Now, once I've done this, I can go and check, is this a trustworthy certificate? Follow? If this is trustworthy certificate based on their sign, blah, 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 then I can proceed. What's the advantage of doing it this way? If I lost this certificate, I cannot recover the private key associated with this communication. This is called Perfect Forward Secrecy. Because even if I lost the key, you cannot go back in time and decrypt the communication.
So the session key is asymmetric key. Now,
The session negotiation key is asymmetric only for this particular session,
okay.
which is then used to create a symmetric key.
Okay.
That is never passed over the network, right?
Or
Okay.
filters all the way down, all the way up. Okay. Now, it gets better. You lost the certificate. How can I tell? So there is something called certificate revocation. I go to the signer, to certificate authority, give me all of the revoked certificates you have. And then I check whatever the item, the certificate that I got is in this list. That list can be pretty big, not one. Can we do something better? Because this also introduces another issue. What happens if I'm already in a bad place? I want to go and talk to Alice, but Charlie is in the middle. I need to verify that she's who she says she is, and that she did it with her key, whatever. So I now need to give a call to Dave. Dave is not answering because Charlie shut down the network. Charlie's calling talking to him, please, whatever. What do you do then? I have two options. Okay, I cannot talk to Dave. I would trust it and move on. I cannot talk to Dave. I cannot trust it. Bye-bye. So practically speaking, I have to go with the first option. Why? Because otherwise there is a really high value denial of service target. Because if I try to go to the secret authority and I can't, and I cannot access that, then if Let's Encrypt is down, half the internet is down. This is a huge issue. It's also a huge issue what happens if there is a big revocation. The certificate authority was hacked. That's going to be really annoying. So the next step is instead of getting the entire certificate location is to ask for specific certificate. This is called Online Certificate Status Protocol, or CSP. And I basically get the certificate. Is it still valid? Yes, no. Still a problem, because now I'm talking to Liel, and in order to talk to Liel, I have to go and talk to Aviv. And I have to do that basically for every request that I get. So first of all, that means that this is a huge load on the certificate authority. Second, this loading is done. So there is something called OTSP statement. What's that? This is when Liel is going to ask Aviv, verify that I'm fine, and then Aviv is going to tell him a ticket for typically 7 days that says this is okay. This is a cryptographic assigned ticket, blah, 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 blah. And then when Liel is talking to me, he's going to send me his certificate, his parent certificate, and the ticket from the certificate authority says that it is okay. So in one shot over the network, I'm doing everything that I need. 1 second.
So
Yeah.
when you have the tickets, you save memory in the disk of the certificates that valid for the next 8 hours, something like that, and then you not need to validate again that.
I can just send it to all of my clients so they can validate in place.
Okay.
That's the point, instead of having to go over the network. That's the difference. Okay, so client certificates. So far, we only talked about this from the client perspective to a server, but it's also the other way around. And it's the exact same process, but there are no rules. The server decides what to do. And for the case of RavenDB, we validate that this is a valid certificate. So it hasn't expired, it's not in the future, or something like that. Someone registered that certificate with us. Or someone registered a certificate with us that has the same public key and the same signer, which then means that this is trusted. Notice that for there is an interesting wrinkle here. The actual code here is pretty complex, and there are a lot of edge cases of condition things that we have to deal with. For example, if you run in the cloud and we need to run maintenance operations, we generate a certificate specifically for this particular class that's only trusted for a very short amount of time that is trusted. and a bunch of other stuff like that. But the last interesting thing is that the server will always trust its own certificate. In a typical cluster, there is one certificate that covers all of the nodes. So inherently, they have the same trust boundary. It's important that we also do that if the certificate is expired. So if you come to me with an expired certificate, typically I want to say bye. I don't want to talk to you. But if it's the same certificate that I'm using, well, if I'm using an expired certificate and you're using an expired certificate, there's no point in security. Let's just accept that. More to the point, this is something that happens if the administrator did not update the certificate. And there is a chicken and egg problem here. I need to run a cluster-wide operation to do that. But I cannot do that if the cluster don't trust each other. So ensure that they actually are trusting each other in this case because, well, a minute ago it was trustworthy, now it's not. Yeah. There's also another fun factor. When are we actually establishing trust in this relationship? At the very beginning. I don't start each day by telling Shachar, please show me that your ID, birth certificate, whatever. Okay. Okay, here is your ID number, and we're good for the rest of our encounter. Next time, I don't know who you are. Show me an ID, but as long as we're in a conversation, okay. In network terms, it means that I establish trust on connection, on TCP connection. That's important. So I connect to Shiran. We change certificate, establish trust, whatever, and then I start using requests. But I may make multiple requests on the same connection. And those connections, on all those requests would already be established trust. This is important because in many cases, if we talk about security at HTTP layer, then we have to establish security on a per connection basis, which is more expensive because we have to do those checks on each connection. Okay, problems. We had a lot of support issues around certificates. We don't trust the old certificate. It happens very frequently if we are running in organizations that generate their own certificates. We can say it doesn't usually happen anymore. Certificate expire, the parent certificate expire, the client certificate expire, all bunch of other stuff can expire. Okay, thankfully that's usually relatively easy. It gets annoying when they don't have the authority to generate the certificate. So try to imagine that you're the IT guy and the person who can generate a certificate is the domain administrator, and he's now off in Switzerland skiing. Okay, stuff like that. One of the things that the primary purpose of your certificate is to verify that the other side is who we say we are. Try to access by IP and not by domain, etc., stuff like that. Another aspect is trusted man in the middle. What the hell is that? Well, consider that I may say that I don't want you to visit Walla. So I'm installing a proxy to prevent you from going to Walla. But I don't know that you're going to Walla because it's encrypted. So I'm going to do the following. I install a root certificate on the Active Directory, which install on all of those machines, because those are the company machines. And then whenever you go out, we generate a certificate that is trusted by your machines because it's trusted by our machines. And there is a Charlie in the middle that decides what to do. It doesn't work with RavenDB. Why is that? Think about it. I need to authenticate to the remote RavenDB server. So it goes like this. I go and talk to Shiran. In the middle, there is a Aviv that transparency intercepts traffic. So I talk to Shiran, Aviv intercept, and send a request instead of him. What's the problem? She wants me to sign a certificate to show that I prove that I own the certificate by signing something. But I cannot do that. So I don't know that Aviv exists. So I cannot send it to her. Why cannot I send it to her? Because part of the encryption, the signing process of the certificate, you sign the session key. So the session key for me and Aviv, the session key of Aviv and Shiran is different. In order to actually show as I have this certificate, Aviv would need to have the client certificate on his machine. Follow? So the fact that they have a trusted man in the middle means that we have to drop the client certificate from the middle. And then Shiran says, hey, I want client certificate, doesn't get that. And anyway. Okay. Other lots of fun. All of this, I have to pass, verify that the server is up, running, whatever. It's incredibly common that we run in environments that have no external access. I can talk to Shiran, but Shiran tell me, oh, you need to verify with Let's Encrypt or GDCert or something like that. I cannot do that. Most of that, it is possible that it takes me a lot of time to come out there. And we had issues where sometimes we ran out of port space or something like that. So sometimes it would fail. It was incredibly annoying. Questions?
From the first very moment,
Yeah.
you said it can happen. What both sides represent? Are they nodes in the cluster or just the RavenDB?
Trusted man in the middle means that I'm trying to talk to a secure RavenDB server.
Who
I'm the client.
Okay.
Doesn't matter. I'm
Okay.
the client, I'm the server, doesn't matter for us. But as a client, I try to talk to a secure RavenDB server. In the middle between me and the server, there is a man in the middle that I trust because he has a root certificate that I trust.
Oh, okay.
Okay, there is a problem here. He cannot present to the server that he has the client certificate.
Yours.
My client certificate.
Yeah, okay.
So we have to have something in the middle that.
So in RavenDB client, we provide us client certificate?
Yeah.
Okay.
The client certificate is what we provide. That's the certificate field in the document store.
Oh, okay.
Yeah. So the reason if we cannot, I'm trying to connect to you on a secure fashion with HPS, is in the statement, whatever, and the error that I get is you don't have a certificate. There is a man in the middle that is trusted, so you don't get the usual error. You get the restrict the certificate error.
Okay.
Questions?
When you generate the client certificate in Raven, you do that by in the same way you generate the server certificate, or this client certificate is signed by
the client certificate is signed by the server certificate. Yes.
Okay, and I know that the server has a list of all the certificates.
Yes.
What happens? Sorry, when the client certificate is expired?
We stop trusting it.
But you need to generate another one, or
yes.
You need to sign the new one by the old one, or how do you do it?
The easiest way to do that would be to, practically speaking, what would tend to happen is that they would generate a new certificate.
Oh, okay.
If they really wanted to, you could sign, you can have an update certificate using the same key, the same issue, whatever, with a different validity period. And it would automatically be trusted by RavenDB. Why does it matter? It matters for a really important scenario. What happens if I have two clusters that need to trust one another? So I have Aviv and Staff, and I establish trust between them, even just from Staff to Aviv. So how do I do that? I take the server certificate from Stav and register that with Aviv. Stav is talking, Aviv says, okay, I'm good. Stav's certificate is going to expire in 3 months. What's going to happen then? Well, she's going to come to Aviv with a new certificate. Aviv says, who the hell are you? Go away. Okay, now that is really cool from a security perspective, less cool from a operation perspective. Try to imagine that you have to remember every 3 months to replace her certificate with him before they do that update. And if we are doing things on a normal fashion, she's going to have a new certificate every 2 months. Sometimes within 2 months or 3 months, we're going to do this replacement. That's going to really, really suck for you, because now we have a problem as a DevOps. When do I update? How do I update? Study is a cluster, so I have to roll it out, etc. So we do it quick. We say whenever we update the certificate using Let's Encrypt, we keep the same private key. And on Aviv's side, he says, okay, this is signed by the same person using the same public key. It's the same thing. Think about it like you have a ID certificate that expires at some point. And I have an image of that certificate, of that ID certificate on my wall. And you went to the Minister of the Interior and got a new certificate. It's not what I have on the wall. From the same country, using the same ID number, whatever, you're still going through.
Yeah.
Okay, that's it. More questions? People in the audience, anything on you? Any question? Oh, awesome. Okay, thank you, everyone.
Thank you.
Bye-bye.